The Arabian Sea at 1:44 a.m. in August carries the specific stillness that precedes nothing in particular, but feels like it precedes something. The air is 32 degrees Celsius, the humidity 77%. The surface chop a residual 1-meter pattern from a wind that has already departed. USS Benfold makes 19 knots on a southerly heading, 66 nautical miles southwest of Bandar Abbas, conducting a transit through the northern Arabian Sea egress corridor after completing a close escort of a liquefied natural gas tanker through the Strait of Hormuz. She has been at general quarters for 28 minutes. The Kish Island ASBM battery that the intelligence community flagged at 1:12 a.m. activated its Khalij Fars targeting radar at 1:16 a.m., and the commanding officer has had the ship at GQ since 1:16:14 a.m. The Khalij Fars launches at 1:22:09 a.m. The terminal approach is near vertical. Mach 3.8, a ballistic profile that arrives from almost directly overhead. The engagement geometry that makes this particular system the most demanding in the Aegis engagement envelope. The ship's SM-6 fires at 1:22:51 a.m. and achieves its first intercept at 1:23:18 a.m. at 14,000 meters altitude. A proximity detonation that disables the Khalij Fars' terminal guidance and fragments the main warhead body. The SM-6's second round, fired at 1:22:58 a.m., intercepts the fragmenting debris at 8,000 meters altitude at 1:23:24 a.m., dispersing the largest pieces laterally. The debris field scatters across a 600-meter radius above the ship. No fragments reach the hull. What reaches the hull are two sequential shock waves. The detonation of each SM-6 intercept, propagating downward from 14,000 and 8,000 meters respectively, arriving at the Benfold's position as a compound overpressure event at 1:23:41 a.m. and 1:23:47 a.m., 6 seconds apart. The overpressure of each individual shockwave at sea level is approximately 0.55 psi, moderate, within the range encountered in previous engagements. But the two shock waves arrive from almost directly overhead, and the 6-second interval means the second shock wave arrives as the hull structure is still responding to the first. The compound dynamic loading, two sequential vertical impulses with a 6-second interval, produces a structural effect on the hull that neither impulse alone would produce. The keel of an Arleigh Burke-class destroyer is a continuous structural member running the full length of the ship's bottom, the primary longitudinal load-bearing element. It does not fracture under 1.1 pounds per square inch of overpressure. The structural margin for the keel against direct overpressure loading is substantially higher than this. What the compound sequential loading produces is not a fracture of the keel, but a transient bending of it. The keel bends vertically during the first impulse, begins to recover, and then receives the second impulse before it has fully returned to its neutral position. The combined effect is a momentary keel deflection of approximately 3.2 millimeters at the ship's midship section. A deflection that is within the keel's elastic range and produces no permanent deformation of the keel itself. But the keel is not alone in the ship's bottom structure. Running parallel to the keel, within the double bottom void space between the keel and the inner hull, are 3 JP5 aviation turbine fuel storage tanks. Tanks F3, F4, and F5, whose inboard faces are integrated into the ship's structural framework. The tanks are bounded on their outboard sides by structural frames and the outer hull, and on their inboard sides by structural bulkheads that separate the fuel cells from the central keel space and from each other. These internal bulkheads, 6mm steel plate welded to the structural frames, are designed to maintain the fuel boundary between adjacent tanks and between the fuel tanks and the void spaces in the double bottom. When the keel deflects 3.2 millimeters at midship, the deflection is transmitted to the structural frames on either side of the keel through the welded connections between the keel and the frame web. The frames flex slightly. The fuel cell bulkheads welded to the frames flex with them. The flexion is small, a few tenths of a millimeter at the bulkhead face. But 3 of these bulkheads have weld joints at the intersection of the bulkhead plate and the frame web, a structural location where welding stress concentrations exist as a normal result of the construction process. The stress concentrations at these 3 weld joints, under the cyclic loading of the compound shockwave, propagate microfractures through the weld at those points at 1:23:47 a.m. The 3 fractures are small. The longest is 7.4 centimeters. The shortest is 3.8 centimeters. None of them extend through the full thickness of the 6 millimeter steel plate. They are through thickness cracks at the weld-toe, where the weld meets the base metal. All 3 fractures are in the boundary bulkheads of tanks F3, F4, and F5. JP5 fuel, which fills these tanks to approximately 73% capacity for the current transit, is now in contact with the fracture faces. At 73% tank fill, the fuel surface is approximately 0.4 meters below the fracture locations. The fractures are in the upper portion of the bulkhead, above the fuel surface. There is no immediate fuel leak. No fuel exits through the fractures at the moment of their formation because the fractures are above the fuel surface level. The fractures connect the fuel cells to the adjacent void spaces in the double bottom. Structural void spaces that run between the fuel tanks and provide inspection access to the tank exteriors. These void spaces are normally dry. They are now open to the fuel vapor space above the JP5 surface in tanks F3, F4, and F5. JP5 fuel vapor, the volatile hydrocarbons that evaporate from the fuel surface at ambient temperature, is now moving through the fractures from the fuel cell vapor space into the adjacent void spaces. The void spaces are confined, unventilated, and in thermal contact with the warm Arabian Sea water outside the hull. At 32 degrees Celsius seawater temperature, the JP5 vapor pressure is sufficient to produce a fuel vapor concentration in the void spaces that will reach the lower explosive limit of JP5, approximately 0.6% by volume. Within approximately 3 hours and 30 minutes of the fracture formation, based on the void space volumes and the vapor transfer rate through the fractures. The chief engineer does not know any of this at 1:23:47 a.m. No alarm has sounded. No sensor has triggered. The hull is intact. No flooding. No fire. No power failure. The engagement has been successful. The ship appears undamaged. He learns about the fractures at 1:51 a.m. when the routine post-engagement structural inspection, a standard procedure the Benfold has drilled 47 times in the past 18 months, reaches the double bottom inspection ports for the F3, F4, and F5 tanks. The inspection is performed by the hull technician using a bore scope through the 4 centimeter diameter inspection ports that provide visual access to the void spaces adjacent to the fuel tanks. The inspection ports are welded fittings in the inner hull. 4 centimeter internal diameter, sealed with a removable threaded plug when not in use, designed to allow visual inspection of the void space and the tank exterior without requiring entry into the void space. The hull technician reports at 1:51:14 a.m. The bore scope in the port adjacent to F3 shows a crack in the bulkhead face, approximately 5 to 6 centimeters in length, at the weld-toe of the frame intersection. The bore scope in the port adjacent to F4 shows a similar crack. The F5 port shows a third crack, smaller. All 3 cracks are visible on the void space face of the bulkhead, the side away from the fuel. The fracture geometry is consistent with through-thickness cracks at the weld-toe. The chief engineer calls DC Central at 1:51:28 a.m. In the next 40 seconds, he establishes the following. The fractures are above the fuel surface level, so there is no liquid fuel leakage. The fractures connect the fuel vapor space to the void spaces. The void spaces have no ventilation. and the JP5 LEL clock has been running for 24 minutes since the fractures formed. He needs to seal the fractures from the void space side. The fractures are in the double bottom, below the inner hull, between the inner hull and the outer hull, in a space that is too small for personnel entry. The Arleigh-Burke's double-bottom void spaces adjacent to the fuel tanks are approximately 35 to 50 centimeters wide, accessible only through the 4-centimeter inspection ports in the inner hull. No person can enter. Any repair must be performed through those ports. The standard approaches for sealing a through-thickness weld crack are welding, which requires direct access to the crack face, a dry environment, and the absence of fuel vapor. All three unavailable in the current void space condition. Rubber patch with clamp, which requires flat hull face access and clamping pressure. Inapplicable in a 35-centimeter void space accessed only through a 4-centimeter port, or epoxy injection, which requires only that the epoxy reach the crack face and fill the fracture volume before curing. Epoxy injection through a 4-centimeter inspection port into a 35 to 50-centimeter void space is not a documented procedure in the ship's damage control library. The DC library references epoxy as a sealing agent for non-structural applications and specifies it as a dry dock or in-port tool, not a field repair. It does not describe injection through a remote port into an inaccessible space. But epoxy is a flowable liquid before curing. 2-component structural epoxy, which the Benfold's DC stores carry for structural patching operations, has a working time of approximately 45 minutes before it begins to cure, and a full cure time of approximately 8 hours at ambient temperature. It can be injected through a tube. It flows to fill whatever volume it occupies. If it reaches the cracked face and fills the fracture, it will cure to a hardness that exceeds the strength of the surrounding steel weld-toe. The question is whether it can be delivered accurately to the crack face from the inspection port. The inspection port is in the inner hull. The crack is in the tank boundary bulkhead, a vertical plate perpendicular to the inner hull face inside the void space. The distance from the inspection port to the crack face varies by location, but is approximately 25 to 40 centimeters for each of the 3 fractures. The chief engineer calls the hull technician at 1:52:04 a.m. I need to inject 2-component structural epoxy through the inspection ports to seal the cracks. I need a delivery catheter, a tube of approximately 5 millimeters internal diameter and at least 45 centimeters in length, flexible enough to maneuver through the inspection port and into the void space. The catheter needs to deliver epoxy under light pressure to the crack face. What do we have? The hull technician responds. The DC stores have 6 millimeter outer diameter flexible nylon tubing used for hydraulic fluid transfer. We have approximately 4 meters of it. Internal diameter is approximately 4 millimeters. The epoxy cartridges are 400 milliliter dual barrel cartridges with a mixing nozzle. The nozzle exit is 8 millimeters diameter. The nozzle won't fit through the inspection port. Cut the mixing nozzle off and connect it to the nylon tubing. The epoxy mixes in the nozzle element itself. The nozzle contains the static mixing baffles. If we remove the cartridge's integral nozzle and attach the nylon tube directly to the cartridge barrel exit, the epoxy components will mix in the tube as they travel through it, provided we ensure they enter the tube simultaneously from both barrels. What tool do we have to drive both barrels simultaneously? The standard epoxy cartridge applicator gun is a dual-barrel plunger device that simultaneously depresses both barrels when the trigger is pulled, ensuring equal flow from both components. The Benfold's DC stores carry one applicator gun, with the mixing nozzle removed and the nylon tube attached directly to the dual barrel exit. The applicator gun will still drive both barrels simultaneously. The mixing will now occur in the tube rather than in the nozzle. The hull technician adapts the applicator gun at 1:52:44 a.m. using duct tape and a threaded reducer fitting from the DC locker to create a connection between the dual barrel exits and the 6 millimeter nylon tube. It takes 4 minutes and 12 seconds. The improvised injector is ready at 1:56:56 a.m. The LEL clock is now running for 34 minutes. Estimated time to reach LEL concern threshold in the F3 void space, the smallest of the three, is approximately 2 hours and 56 minutes. The overall window is approximately 3 hours from now. The chief engineer assigns 3 injection teams: the hull technician for F3, the damage controlman for F4, and the machinist's mate for F5. The injection procedure: insert the bore scope through the inspection port. Locate the crack face visually. Mark the catheter insertion depth with tape to establish the crack distance. Withdraw the bore scope. Insert the nylon catheter to the marked depth. Advance the catheter tip to the crack face. Begin epoxy injection while slowly withdrawing the catheter, allowing the epoxy to fill the crack from the deepest point outward. The bore scope work at F3 establishes the crack face distance at 31 centimeters from the inspection port edge. The catheter is inserted at 1:58:33 a.m. The injector gun is operated by a second team member. One person holds and advances the catheter, the second operates the gun. The 2-component epoxy begins flowing at 1:58:41 a.m. The first problem emerges immediately. The epoxy, flowing through a 4 mm internal diameter nylon tube at approximately 35 centimeters of length, encounters a flow resistance that requires significant gun trigger pressure to maintain flow. The hull technician holding the catheter reports at 1:59:04 a.m. Flow is minimal. The gun operator can't maintain the trigger pressure for sustained flow. The epoxy is moving slowly but not reaching the crack face continuously. The chief engineer responds. Maintain the catheter position. Switch to intermittent pump strokes. Release the trigger fully between each stroke to let the operator's hand recover. The flow rate will be slower but sustainable. We need continuous delivery to the crack face, not fast delivery. The F3 injection proceeds with intermittent strokes. The bore scope, reinserted alongside the catheter tube on its second entry, confirms at 2:01:14 a.m. that epoxy is visible at the crack face, a dark bead extending along the lower portion of the crack. The catheter is slowly withdrawn at 2:01:18 a.m., allowing epoxy to fill the crack from the bottom upward. The bore scope shows the epoxy advancing along the crack face as the catheter retreats. Complete coverage of the F3 crack visible at 2:03:41 a.m. F3. Epoxy injection complete at 2:03:41 a.m. Time since fracture formation, 39 minutes. F4 injection has been running in parallel since 1:59:17 a.m. The F4 crack face is at 38 centimeters. Longer path, higher resistance. The damage controlman switches to a 2-person trigger arrangement at 1:59:44 a.m. Both the damage controlman and his partner grip the trigger simultaneously, combining hand strength to maintain sustained flow. Epoxy reaches the F4 crack face at 2:01:58 a.m. F4 crack fully covered at 2:04:29 a.m. Inspection port plug replaced at 2:04:33 a.m. F5 injection encounters the second problem at 2:03 a.m. The improvised catheter adapter, the duct tape and reducer fitting connection between the dual barrel exits and the nylon tube, begins to leak. Epoxy is seeping around the adapter fitting rather than flowing through the tube. The machinist's mate reports at 2:08 a.m. Epoxy is leaking at the adapter. The duct tape connection is not holding the pressure. The chief engineer at 2:12 a.m. Withdraw the catheter and stop the injection. Reseal the adapter. Do you have hose clamps in the DC locker? Yes, 2 20mm hose clamps. Apply both hose clamps over the duct tape adapter. Stack them in the same position to double the clamping force. Then restart. The hose clamp application takes 2 minutes and 19 seconds. 5 injection restarts at 2:02:31 a.m. The adapter holds. The F5 crack face is at 28 centimeters. The delay from the adapter failure has compressed the time window but has not exhausted it. Epoxy reaches the F5 crack face at 2:03:48 a.m. F5 crack fully covered at 2:05:44 a.m. Inspection port plug replaced at 2:05:48 a.m. All 3 fractures sealed with epoxy injection at 2:05:48 a.m. Time since fracture formation, 41 minutes and 1 second. Post-injection bore scope confirmation of all 3 ports at 2:08:44 a.m., 2:09:02 a.m., and 2:09:17 a.m. shows continuous epoxy coverage with no visible gaps. The epoxy is visibly setting. Its surface sheen has transitioned from liquid reflective to matte, indicating the initial cure stage has begun. Void space JP5. Vapor concentration measured at all 3 ports at 2:11 a.m. F3, 2.1% LEL. F4, 1.8% LEL. F5, 1.6% LEL. All below the 10% threshold. The fracture sealing has stopped the vapor transfer. Readings at 2:30 a.m. F3 at 1.2%. F4 at 0.9%. F5 at 0.8%. Declining. Epoxy cure confirmed at 5:30 a.m. All 3 sealed areas at full cure hardness. No cracked face visible through the epoxy surface. No gap or unbonded area. The ship transits to Bahrain under its own power at 20 knots. Arriving at 8:14 a.m. The chief engineer was asked at the debrief whether the decision to attempt the epoxy injection was driven by the LEL risk or by the structural concern. He said the LEL risk. He said the fractures themselves were not a structural emergency. 3 5 to 7 centimeter cracks in 6 millimeter fuel cell bulkheads above the fuel surface level are a maintenance problem, not a survival problem. The LEL accumulation in the confined void spaces was the emergency. At the rate of vapor transfer through the fractures, the F3 void space would have reached 10% LEL in approximately 3.5 hours. It would have reached 50% LEL, the midpoint of the explosive range, in approximately 5.5 hours. The ship would have been transiting toward Bahrain with 3 void spaces in the double bottom developing toward explosive atmosphere. He said the epoxy injection was not the most elegant solution. He said it was the only solution available in the ship's current inventory that could reach the cracked faces without requiring void space entry, without requiring welding in a fuel vapor environment, and without requiring dry dock facilities. He said the duct tape adapter failure on F5 was predictable in hindsight. The hose clamps should have been on the initial assembly. He said the 30-second failure response and the 2-minute and 19-second reassembly was time available in the 3-hour window, but would not have been available if the LEL had been closer to the threshold when the injection began. 2 sequential shockwaves at 1 point, 1 pounds per square inch compound, vertical overpressure at 123.41 and 123.47 a.m. Keel deflection, 3.2 millimeters at midship, transient, elastic recovery. Fuel cell boundary bulkhead fractures, 3 locations, F3, F4, and F5. Weld-toe fractures at frame intersections, 3.8 to 7.4 centimeters each. No flooding, no fuel leakage, fractures above fuel surface. Vapor transfer to void spaces began at fracture formation, LEL window. Approximately 3.5 hours to concern threshold. Fractures identified at 1:51:14 a.m., 27 minutes after formation. Improvised epoxy injection catheter ready at 1:56:56 a.m. All 3 fractures sealed at 2:05:48 a.m. 41 minutes after fracture formation. Void space LEL readings post-injection. 1.6 to 2.1% declining. Epoxy cure confirmed at 5:30 a.m. Ship status, operational. The nylon tubing that served as the epoxy injection catheter for all 3 sealing operations is 6 millimeters outer diameter, 4 millimeters internal diameter, a standard hydraulic fluid transfer tubing from the ship's damage control stores. It is used normally for running temporary hydraulic fluid lines during machinery space repairs. Its nominal purpose is to carry hydraulic fluid from a portable supply to a fitting that needs lubrication or pressure priming. It has no listed damage control function. It is in the stores because hydraulic fluid transfer is a routine maintenance requirement, and the tubing is the cheap, flexible cut-to-length solution for doing it. The epoxy that cured in the F3, F4, and F5 bulkhead fractures hardened to a compressive strength that exceeds the surrounding steel by approximately 15% in the initial cure state. The fractures are sealed. The vapor transfer has stopped. The void spaces are clear. The ship returned to Bahrain under its own power. The keel that bent 3.2 millimeters at 1:23:47 a.m. does not know it was ever bent. Steel in the elastic range has that quality. It deforms and returns, and the deformation leaves no trace in the primary structure. The trace it left was in the 3 weld toes at the 3 intersections, where the stress concentrations from the construction process had been waiting, patient and invisible, for a load that was large enough and fast enough and vertical enough to find them. The compound shockwave from overhead found all 3 in the same 6 seconds. The nylon tubing found all 3 in the 41 minutes that followed.